The stars are whispering a secret, and we are finally learning to listen. Subtle patterns in starlight are cosmic breadcrumbs pointing toward vast, unseen processes operating between galaxies. This video will give you a new understanding of the universe, revealing it as a deeply interconnected and dynamic web. We will uncover how mysterious alignments and rhythmic pulses of light challenge everything we thought we knew about cosmic evolution. You will learn how astronomers decode these stellar messages to probe the hidden architecture of the cosmos. What invisible forces do you think are shaping the light from the stars? Every pinprick of light in the night sky is a detailed cosmic communique. Starlight is far more than simple brightness. It is a dense stream of information, a narrative written in photons after their epic journey across the cosmos. To read this story, astronomers use a tool called spectroscopy, which splits the light into its constituent colors, creating a spectrum much like a rainbow. Within that rainbow, you find unique patterns, dark lines where specific colors are missing and bright lines where others shine with extra intensity. These lines are the fingerprints of the universe's elements. A dark line here means hydrogen atoms in the star's outer atmosphere absorbed that specific color of light, while a bright line over there reveals helium being excited. From this, we can decipher a star's chemical composition, its temperature, its age, and even whether it is moving toward us or away from us. For over a century, this is how we have understood the lives of individual stars. But now, a new chapter is being written. Scientists are looking beyond the story of single stars and are instead examining the collective light from thousands, even millions of them. They are finding that the fingerprints are not completely random. There are subtle, large-scale correlations in the data, statistical patterns in how the light appears that cannot be explained by the stars themselves. The light seems to carry an imprint from its long voyage through the vast, seemingly empty expanses between galaxies. It is as if the void itself is leaving a faint signature on the starlight, a whisper of unseen processes that operate on a scale we are only beginning to fathom. This faint cosmic whisper leads us directly to our first profound pattern, a mystery written in the very color of starlight itself. We have long understood that the light from distant galaxies is stretched, shifting toward the red end of the spectrum, a phenomenon we call redshift. For decades, the primary explanation has been the expansion of the universe, a Doppler-like effect as galaxies recede from us. But what if this story is not the whole truth? When astronomers analyze the redshifts of millions of galaxies, they find something deeply puzzling. The values are not scattered randomly, as one might expect from a uniformly expanding cosmos. Instead, they appear to cluster in curious groupings, showing subtle periodicities, almost like a hidden rhythm in the data. It is as if the universe is playing a chord progression on an instrument of unimaginable scale, and we are only just beginning to hear the tune. One compelling idea is that these redshift anomalies are the imprint of vast, unseen structures. Picture the cosmos not as a sparse collection of isolated galaxies, but as a web of immense filaments and great walls, a cosmic architecture on a scale that defies easy comprehension. The gravitational pull of these colossal formations could subtly tug on light, adding another layer of redshift, another note to the cosmic chord. This would mean our standard measurement for cosmic distance and expansion, a tool we have relied on for a century, might require a subtle recalibration. The map we have been using is good, but it may be missing some of the largest continents on the cosmic globe. An even more radical suggestion is that these patterns point toward physics we have not yet discovered, processes that affect light over its billion-year journey across gigaparsecs of space. The empty void between galaxies may not be entirely empty. It could be filled with a subtle energy or a field that interacts with light in a way we do not yet understand, leaving its signature in these statistical curiosities. This pattern challenges the very foundations of how we measure the universe, forcing us to ask if we are truly seeing the cosmos as it is, or if unseen forces are gently bending the rules, leaving their trace in the light we so carefully collect. And if the fabric of space-time itself can be subtly distorted, what other illusions might it be creating? These subtle distortions in starlight find a parallel in the very motion of the stars themselves. For centuries, we have charted the slow, steady drift of stars across the celestial sphere, a measurement known as proper motion. Each star was thought to be an independent voyager, tracing its own isolated path through the galaxy's gravitational field. But modern data has shattered that solitary picture. Precision missions like Gaia, which maps the positions and movements of over 1 billion stars, have uncovered something deeply strange. Astronomers are finding that groups of stars separated by staggering distances, stars that should have no physical connection, sometimes move in subtly synchronized ways. Their proper motions show faint but statistically significant correlations. It is as if an invisible conductor is guiding their motion, a silent rhythm in the dark. How can stars light years apart, not bound by gravity, appear to dance to the same tune? The answer may lie not with the stars, but with the space between them. One compelling idea is that we are not seeing the true motion of the stars, but rather an illusion painted on the sky by unseen mass. Imagine a vast, transparent lens floating in the intergalactic void, a structure built from dark matter or a cluster of ancient primordial black holes. As the light from distant stars travels for millennia to reach us, it passes through this invisible lens. The lens's gravity bends the starlight, subtly shifting the apparent position of each star. If the lens itself is moving, it shifts the positions of all the stars behind it in a coordinated way, creating the ghostly impression that the stars themselves are moving together. This is not a true motion, but a cosmic mirage on an epic scale. These correlated motions, therefore, become a shadow play, revealing the presence and movement of the most elusive structures in the universe. They offer us a new way to chart the distribution of dark matter, to feel out the shape of the cosmic web itself by watching how it distorts the motions of 1 billion pinpricks of light. This grand illusion forces us to ask what other truths about the cosmos are hidden, not in the objects we see, but in the silent, shifting spaces between them. The rhythm of the cosmos deepens with a third, even more enigmatic pattern, found in the most brilliant beacons of the ancient universe. Quasars, the furious cores of distant galaxies powered by supermassive black holes, are known for their chaotic flickering. Their light should be a textbook example of random turbulence, a storm of incalculable energy. Yet, when astronomers patiently chart their brilliance over years and decades, a strange signal emerges from the noise. The light curves of some quasars show distinct, periodic dimming events. These are not the brief, telltale eclipses of orbiting planets, but vast, slow rhythms playing out over timescales that dwarf human lifespans. A quasar might fade and brighten again on a schedule spanning years, only to repeat the cycle with eerie precision decades later. Such immense regularity points to a cause of almost unimaginable scale, something far beyond the chaotic engine of the quasar itself. What could possibly cast a shadow that large and that predictable? One compelling explanation lies in the great dark between the galaxies. Imagine a vast, coherent structure, like a wave of unusually dense gas or a sprawling, ordered swarm of ancient compact objects, drifting through the intergalactic medium. As this immense formation moves on its cosmic course, it could periodically drift directly into our line of sight to the quasar. For a time, it acts like a semi-transparent screen, dimming the brilliant light in a way that appears, from our distant vantage point, as a slow, rhythmic pulse. This would mean the space between galaxies is not a uniform and featureless void, but is instead textured with colossal, drifting formations that we have only just begun to detect by the shadows they cast. An even more profound possibility suggests that these light curves are not recording the passage of a physical object, but a subtle oscillation in the fabric of reality itself. Some theoretical work explores whether the fundamental constants of nature, the very numbers that dictate the strength of physics itself, could oscillate over cosmic timescales. If true, such a slow, universal vibration could subtly alter how light is produced or absorbed over its billion-year journey, creating a periodic signal imprinted on the most distant sources we can see. This rhythmic dimming forces us to confront a universe that is not only expanding but may also be breathing, its deepest laws potentially humming with a vibration we can only detect by watching the oldest lights slowly, rhythmically, fade and return. To truly grasp these cosmic patterns, we must finally meet the universe's silent partner, dark matter. We know it makes up the bulk of the cosmos, its gravitational pull sculpting galaxies and guiding their immense clusters. Yet its influence may extend far beyond the boundaries of visible matter, into the great voids between galaxies. Imagine dark matter not as isolated halos around galaxies, but as a pervasive, intricate network, a cosmic scaffolding stretching across the universe. This vast, invisible web could be subtly shaping the very light that travels through it. As photons from a distant quasar or a far-off galaxy journey for billions of years, their paths weave through this unseen architecture. The gravity of the dark web acts as a complex array of lenses, each one too faint to detect on its own, but together creating a collective effect. These lenses do not create sharp, dramatic arcs. Instead, they impart a gentle, statistical warping, a coherent distortion in the apparent shapes and brightnesses of millions of background galaxies. This technique, known as weak gravitational lensing, allows us to feel out the shape of the dark universe. The subtle correlations in starlight, the synchronized motions, the rhythmic dimming, all these patterns we have been deciphering could be the high-resolution tracers of this dark architecture. They are the faint shadows cast by the hidden mass of the cosmos, a ghostly imprint revealing the structure of everything we cannot see. This concept leads us directly to one of the most profound mysteries of all, the phenomenon of cosmic flows, where entire galaxies seem to be pulled by forces beyond the visible universe. This alignment of distant galaxies presents a fourth, and perhaps the most baffling, pattern of all. Think of light as a wave, a tiny vibration traveling through space. Normally, these vibrations are chaotic, pointing in every direction. But when light becomes polarized, its vibrations are mysteriously organized, all swaying in the same preferred plane. We see this in everyday life with polarized sunglasses, which cut down on glare by blocking light waves oscillating in a specific direction. Now, extend that idea across the cosmos. Astronomers studying the radio light from countless galaxies have found something that should be impossible. The polarization angles of galaxies separated by unimaginable voids, by billions of light-years of emptiness, show a faint but undeniable degree of alignment. It is as if countless lighthouses, scattered across an endless ocean, have all decided to flash their beams in the same direction, despite having no way to communicate. How could the magnetic fields or the internal physics of galaxies so far apart possibly coordinate in this way? There is no known force that could link them across such cosmic distances. This coordination must be written into the fabric of their journey, not their source. One profound possibility is that we are seeing a fossil, a relic from the universe's first fleeting moments. During the period of hyper-fast expansion known as inflation, the entire cosmos may have been seeded with a fundamental alignment, a primordial preference for direction that was then frozen into the structure of spacetime itself. Billions of years later, as galaxies formed and evolved, this ancient signature was imprinted on their light, a ghostly echo of creation. An equally compelling idea is that the vast emptiness between galaxies is not a passive backdrop. The intergalactic void could be filled with a subtle, all-pervading field or a structured medium that gently rotates the polarization of light traveling through it. Over billions of years, this universal interaction would coax the light from wildly different sources into a faint, coherent alignment. This suggests the vacuum of space itself is not truly empty, but possesses a quantum texture with active properties that can organize the universe on its grandest scales. The silent, dark spaces between everything may be humming with a fundamental order, one we are only beginning to perceive by reading the subtle, coordinated whispers of ancient starlight. So the space between galaxies is not truly empty. It is filled with an ultra-thin, superheated plasma, a cosmic fog we call the intergalactic medium. For decades, we saw this medium as a passive backdrop, a simple stage upon which the drama of galaxies played out. But what if this fog is an active participant, a cosmic filter that subtly sculpts the light passing through it? We already see one dramatic signature of this filter in the light from the most distant quasars. As that brilliant light travels through the fog, hydrogen atoms in the plasma snatch away very specific colors, creating a unique pattern of dark absorption lines in the quasar's spectrum. Astronomers call this the Lyman alpha forest, a beautiful name for a complex tracer map of the universe's hidden structure. But the influence of this intergalactic fog may be far more subtle and pervasive. Imagine the entire expanse between galaxies filled with gentle ripples, tiny fluctuations in the density and temperature of this primordial plasma. These ripples would be too faint to see individually, but their collective effect could cause a phenomenon we might call intergalactic scintillation. Just as Earth's atmosphere makes stars twinkle, these vast, slow ripples in the intergalactic medium could cause a faint, correlated twinkling across the sky, a whisper of shimmer imprinted on the light from entire galaxy clusters. This would not be a random flicker, but a patterned one, its rhythm dictated by the largest structures in the cosmos. Even more intriguing is the possibility that this cosmic fog is magnetized. What if the voids are threaded with vast, coherent magnetic fields, relics from the universe's violent birth? Or what if they are crossed by steady streams of ultra-low-energy particles, flowing along the cosmic web's invisible filaments? Such features would be too diffuse to detect directly, but they would leave a subtle signature on the light that journeys for billions of years through them. They could gently twist the polarization of that light, or ever so slightly alter its color in a coordinated way across the sky. The intergalactic medium, therefore, is not a simple void. It is a complex, dynamic filter, and every beam of starlight we collect is a palimpsest, a layered record of its long voyage through this cosmic haze. The patterns we are finding, the synchronized motions and the aligned polarizations, may be the integrated effect of this epic journey. They are telling us a story about the history of the universe itself, especially the epoch of reionization, when the first stars and galaxies lit up and flooded the cosmos with radiation, fundamentally changing the nature of this intergalactic fog. The light we see today carries the memory of that ancient transformation. So when we detect a strange correlation or a puzzling rhythm in starlight, we are not just looking at the star. We are reading a diary, its entries written by every particle, every field, and every ripple the light encountered on its billion-year journey to us. Even the darkness between the stars holds a faint, pervasive glow. This is the cosmic infrared background, a whisper of warmth that fills the entire sky, the accumulated heat from countless galaxies across the entirety of cosmic time. It is the universe's baseline hum. For a long time, we assumed this background was smooth and uniform, a perfect cosmic canvas, but our most sensitive telescopes have revealed it is not smooth at all. It is subtly textured, filled with faint, lumpy patterns known as anisotropies. These are ripples in the cosmic fog, fluctuations in brightness that are too pronounced to be explained by the galaxies we already know and can see. It is as if we are listening to a vast choir and can hear the collective voice, but our instruments are picking up extra harmonies from singers hidden in the shadows. So who or what are these hidden singers? One profound possibility is that we are detecting the collective light from the very first galaxies to ever form. These primordial stellar systems, born in the universe's raw youth, would be too faint and distant to see as individual points of light. Yet, their combined, smoky glow could be imprinted as these excess ripples in the infrared sky, a fossilized imprint of the universe's first dawn. We would literally be seeing the ghostly afterimage of creation itself. Another intriguing idea points not to stars, but to the great voids between them. What if the intergalactic medium, that cosmic fog, is not just hot gas? What if it is also filled with vast, diffuse clouds of cold dust drifting in the darkness? These clouds, warmed by the ambient starlight of the universe, would glow faintly in the infrared. Their intricate, web-like distribution would create exactly the kind of lumpy patterns we observe, tracing the architecture of the cosmic web in thermal radiation. But the most enigmatic possibility connects this glow to the universe's greatest mystery. The patterns could be a signature of dark matter itself. Certain theoretical models suggest that dark matter particles, when they collide, could annihilate each other, releasing a faint spray of energy. Or they might slowly decay over eons. Either process would inject a subtle, diffuse light into the cosmos, a light that would be woven into the very fabric of the infrared background. The specific pattern of the fluctuations could be the calling card of these invisible particles. So when we stare into this faint infrared glow, we are not just looking at ancient starlight. We are potentially reading a document that records the universe's first stellar flickers, the distribution of hidden cosmic dust, and the very nature of the dark matter that shapes our reality. It is a single, whispering signal carrying multiple epic stories, waiting for us to learn how to separate its threads. The bending of light by gravity is one of the universe's most elegant tricks. We have all seen the spectacular images, the perfect circles of distorted light known as Einstein rings, where a massive galaxy cluster acts as a cosmic magnifying glass. But these dramatic events are only the most obvious examples. For every one of those, there are countless instances of weak gravitational lensing, a subtle warping so faint it is invisible to the naked eye. Here, the lens is not a single, dense cluster. Instead, it is something far more vast and diffuse, like an immense filament of the dark matter web. Its gravity is too weak to create rings or arcs, but it does something equally profound. It imparts a tiny, coherent distortion to the shapes of millions of background galaxies, a systematic shearing that aligns them in a faint, statistical whisper across the sky. This correlated shear is the ghostly fingerprint of the cosmic scaffolding itself, a map of the unseen mass drawn not with ink, but with the twisted light of distant island universes. This leads to an even more speculative yet fascinating idea. Light, as we know, behaves as both a particle and a wave. What if the lensing phenomenon is not just about the bending of rays, but about the interference of waves? Imagine the light from a distant quasar traveling for billions of years. On its journey, it does not pass a single lens, but a complex, multi-scale landscape of dark matter clumps and filaments. This would be like a beam of light passing through a cosmic tapestry woven with threads of varying thickness. In theory, this could create a delicate interference pattern, where the light waves reinforce or cancel each other out depending on their path. This effect, governed by wave optics, would imprint a unique, frequency-dependent signature on the light, a kind of cosmic echo. While our current telescopes lack the precision to detect such a subtle shimmer, its potential discovery would open an entirely new window onto the cosmos, allowing us to probe the texture of the dark universe with a fineness we can currently only dream of. These lensing echoes, from the faint shear of galaxies to the theoretical hum of wave interference, are among our most direct probes of all the mass in the universe. Their study even brushes against one of cosmology's most exotic predictions: cosmic strings. These are theoretical, flaw-like defects in spacetime, unimaginably thin yet incredibly dense, left over from the universe's earliest moments. A cosmic string drifting between us and a distant galaxy would act as a unique gravitational lens, creating a telltale double image. While never conclusively observed, the search for their signature is part of this broader quest to decode every subtle pattern imprinted on Starlight by the hidden architecture of reality. Each distortion, each tiny alignment is a message, a clue about the true, shadowy structure of everything that exists. Our cosmic distance ladder, the very tool that revealed an accelerating universe, might be built on a subtle illusion. Type 1, a supernova, have been our most trusted standard candles, the brilliant explosions of white dwarf stars that all reach nearly the same peak brightness. This consistency is what allowed us to measure the vast expanses of the cosmos and discover the shocking influence of dark energy. Yet, when we look closer, a quiet unease emerges. Astronomers have found that these beacons are not perfectly uniform after all. Their peak brightness and the precise shape of their fading light curves show faint, but statistically significant, correlations with their location in the cosmos. A supernova occurring inside a massive galaxy cluster might appear systematically different from one exploding in a lonely, isolated galaxy. The light itself seems to carry a memory of the environment it was born into. One immediate thought is that the progenitor stars themselves are subtly different. Perhaps the age or composition of the white dwarf varies depending on the cosmic neighborhood, leading to small variations in the explosion. This would be a fascinating discovery about stellar evolution, but it is a problem we could calibrate for. A far more profound possibility is that the supernova are perfect, but their light is not. What if the light's long journey to us is subtly changing it in ways that depend on the path it takes? The vacuum of space is not truly empty. It is a seething quantum foam, and some theories suggest its properties could vary slightly across the universe, like a landscape with gentle hills and valleys. As light travels through different regions of this quantum terrain, its passage could be minutely altered. This would mean the dimming we attribute entirely to cosmic expansion and dark energy is actually a composite signal. Part of it is the universe stretching, but another part could be the cumulative effect of the light's voyage through a textured vacuum. Our most fundamental tool for measuring the cosmos would then require a profound recalibration. The very nature of dark energy, the mysterious force driving cosmic acceleration, would be thrown into question. Is it a real energy permeating space, or are we seeing a grand mirage created by the uneven transparency of the universe itself? The trusted flicker of a dying star thus becomes a probe not just of distance, but of the deepest, most elusive nature of reality. The ultimate signature of creation may be written not in light, but in the very curvature of reality. To find it, we must look back to the universe's first fleeting fraction of a second, to a period of hyper-fast expansion called inflation. This violent birth is theorized to have shaken the fabric of spacetime, sending forth ripples known as primordial gravitational waves. These are not waves of light or sound, but literal distortions in the dimensions of the cosmos, stretching and squeezing space itself as they travel. While we cannot see these waves directly, they left a ghostly imprint on the oldest light we can observe, the cosmic microwave background. As this primordial light traveled through the rippling spacetime, the gravitational waves subtly twisted its polarization, imposing a unique curl-like pattern known as B modes. Finding this pattern is the holy grail of modern cosmology. It would be a direct message from the universe's first instant, confirming the physics of inflation and revealing the processes that set the initial conditions for everything that followed, from the grandest galaxy cluster to our own local star. The hunt for this signal is a monumental technical challenge. The curl pattern is incredibly faint, a whisper buried under a roar of interference. It is masked by the polarized light from interstellar dust within our own galaxy, which can mimic the very signal we seek. Researchers must build exquisitely sensitive telescopes, often placed at the driest, highest points on Earth or in orbit, to have any hope of isolating this cosmic fossil from the foreground noise. This search connects the largest scales of the cosmos with the most fundamental laws of physics, pushing the limits of our technology and our understanding. The detection of these primordial B modes would be the ultimate confirmation of an unseen process, a direct observation of the moment the cosmic web was woven, its vibrations forever etched into the background hum of the universe. Our own cosmic neighborhood hides a startling secret, a vast emptiness that may be distorting our entire view of the universe. We appear to reside inside a colossal bubble of space known as the KBC Void, a region of staggering scale that is significantly emptier of galaxies than the cosmic average. This is not a small local anomaly, but an underdensity spanning over 2 billion light-years, a true cavern in the cosmic web. For generations, our foundational assumption has been the cosmological principle, the idea that on the largest scales, the universe is smooth and homogeneous, looking roughly the same from any vantage point. The existence of such a massive local void directly challenges this core tenet. It forces us to confront a profound question. Are we truly seeing the universe as it is, or are we looking out from a place of unusual quiet, misinterpreting the grand cosmic symphony because we are sitting in a silent hall? This local environment has a direct and measurable impact on one of cosmology's most pressing puzzles, the Hubble tension. This is the stubborn discrepancy between the measured rate of the universe's expansion using data from the early universe, like the cosmic microwave background, and the rate measured locally using relatively nearby objects like supernova and Cepheid variable stars. The two methods, one looking deep into the infant cosmos and one surveying our modern neighborhood, consistently yield different answers. The void offers a compelling explanation for this rift. Think of space itself as an elastic fabric. In a dense region packed with galaxies and their associated dark matter, the gravitational pull of all that mass acts as a drag, slightly resisting the overall expansion. In an underdense void, however, there is far less gravity to hold things back. The space within the void expands faster than the cosmic average. Our local measurements of the Hubble constant are therefore not measuring the true global rate of expansion. They are measuring the faster local expansion rate inside our bubble. We have been using a local yardstick to measure a global property, and the numbers have not matched because our yardstick is not standard. The pattern of galaxy densities and their correlated motions in our vicinity becomes a critical clue, a shadow cast by the unseen architecture of the cosmic web. The light from distant supernova, our trusted standard candles, is interpreted under the assumption of a uniform universe. But if that light must travel into and then out of our local void, its journey is subtly altered, potentially biasing our perception of its brightness and distance. The Hubble tension, therefore, may not be a sign of new physics or a flaw in our models. It could be the signature of our own unusual address, a reminder that our viewpoint is not perfectly average, and that the grandest truths of the cosmos can be obscured by the silent, empty spaces closest to home. This fundamental graininess of reality could be the ultimate source of the patterns we see. The universe at its smallest scale may not be smooth and continuous, but rather a turbulent, frothing sea, a concept physicists call quantum foam. This is the theoretical texture of spacetime itself, a dizzying landscape emerging from the attempt to unite Einstein's gravity with the probabilistic rules of quantum mechanics. In this view, The very fabric of space and time is not a silent stage but a bubbling, energetic medium, constantly fluctuating at scales a billion trillion times smaller than an atom. For a single photon on a short journey, this foam is irrelevant. But for a particle of light traveling for billions of years across the cosmos, these minuscule bumps and wobbles in the road could add up. The journey is not a straight line on a perfect surface, but a path across a frothing ocean, with each tiny wave subtly jostling the photon. Over an epic cosmic distance, this could lead to a very slight blurring of the image or a subtle smearing out of different light colors. A perfectly sharp point of light from a distant quasar might arrive at our telescopes ever so slightly fuzzy. We are searching for this cosmic blur. Astronomers use the most energetic light in the universe, gamma rays from distant quasars, as their ultimate test signal. These photons pack a tremendous punch, and their short wavelengths make them exquisitely sensitive to the tiniest bumps in the road of spacetime. If the quantum foam is churning at a certain level, it would randomly perturb the paths of these gamma-ray photons. Some would arrive a fraction of a second later than others, smearing out the sharp flare of a quasar explosion. The astonishing fact is that the images we see remain incredibly sharp. The light from these unimaginably distant cataclysms arrives with a crispness that challenges many models of a foamy spacetime. The absence of blurring tells a profound story. It places strict limits on how frothy the universe can be, ruling out some of the wilder theoretical possibilities. In this way, the ancient light from a dying star becomes a precision tool, a probe that allows us to feel out the texture of reality at the Planck scale, a realm forever beyond the reach of any particle accelerator. We are using the universe itself as a laboratory, and Starlight is our data stream from the frontier of quantum gravity. This incredible bridge, from the largest cosmic scales down to the smallest possible vibrations of spacetime, reveals another hidden force that may be woven through the void, a force that can organize the chaos. The cosmos just sent us a message written in a language of pure energy. Fast radio bursts are some of the most violent and mysterious events in the universe. Brief blasts of radio waves so powerful they outshine entire galaxies for a single, fleeting millisecond. They come from billions of light years away, and as these pulses race across the cosmos, they carry with them a subtle, encoded diary of their journey. The key to reading that diary lies in a phenomenon called dispersion. Think of the burst as a chord played on a cosmic piano, with high notes and low notes all struck at the same instant. As this chord travels through the sparse, ionized gas that fills the space between galaxies, it begins to stretch out. The high-frequency notes, the treble, slip through more easily and arrive at our telescopes first. The lower frequencies, the bass, lag slightly behind as if wading through a thicker medium. This time delay, this dispersion measure, should be a perfect cosmic odometer. The greater the delay between the high and low notes, the more intergalactic material the burst has traveled through, and thus, the farther it has come. But the universe loves a good mystery. For some of these bursts, the dispersion measure is far too high. The bass notes are arriving much later than they should, given the estimated distance to their home galaxy. It is as if a musical note from a nearby hilltop took an unexpectedly long time to reach your ears, suggesting it traveled through an invisible, silent forest you never knew was there. This anomalous dispersion points to a hidden component of the cosmos. The burst must have passed through vast, unseen clouds of ionized plasma that our current maps of the universe do not include. These are not the familiar clouds within galaxies, but colossal, diffuse halos extending far beyond the visible edges of galaxies, or perhaps immense, isolated structures of superheated gas adrift in the profound emptiness of the intergalactic void. These phantom clouds, these invisible oceans of free electrons, have now been revealed by the distorted echo of a cosmic explosion. Each anomalous fast radio burst becomes a single, brilliant flash of lightning in a dark landscape, momentarily illuminating the hidden topography of the cosmos. By collecting enough of these flashes, astronomers are beginning to census the invisible, to map the distribution of this missing plasma. This is how we are learning that the great voids are not empty at all, but are textured with ethereal seas of matter, their presence recorded only in the delayed bass notes of the universe's most powerful and enigmatic signals. This ancient light is the ultimate cosmic fossil, a snapshot of the universe in its infancy. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a bath of radiation that fills every cubic inch of space. It is the oldest light we can observe, emitted when the universe was a mere 380,000 years old, a time when it cooled enough for atoms to form and light to finally travel freely. For decades, we have known this background is not perfectly smooth. It is imprinted with a pattern of incredibly subtle temperature fluctuations, tiny variations hotter and colder than the average by mere millionths of a degree. These anisotropies are the most important blueprint in existence. They are the gravitational seeds, the slight overdensities and underdensities that, over billions of years, grew into every galaxy, every cluster, and every vast cosmic void we see today. This pattern is the initial condition for our entire cosmic story. Yet, this primordial canvas also holds clues to events that happened long after its creation. As this ancient light travels across the cosmos to reach us, it interacts with the structures that grew from its own imperfections. One remarkable effect occurs when CMB photons pass through the immense clouds of hot gas that surround giant galaxy clusters. The energetic electrons in this gas give the photons a slight energy boost, a process known as the Sunyaev-Zeldovich effect. This creates a distinct, shadowy imprint on the CMB map, a specific cold spot that reveals the presence and properties of the cluster, effectively allowing us to use the ancient light as a backlight to illuminate the modern universe. This is how the fossil light helps us take a census of the largest structures in space. But the most profound secrets may lie in the pattern's finer details. The standard model of cosmology predicts that the CMB's fluctuations should be mostly random or Gaussian. Astronomers are now searching for subtle deviations from this randomness, for strange alignments or specific, non-Gaussian patterns etched into the background. Finding such a signal would be revolutionary. It could be the long-sought evidence for exotic physics from the universe's first moments. It might reveal the existence of cosmic strings, unimaginably dense flaws in spacetime that could have acted as gravitational lenses for the infant light. Or it could point to an even more mind-bending possibility, that our universe collided with another bubble universe in the vast multiversal foam during its hyper-expansion, a collision that would have left a bruise on the CMB. This faint, cold light is therefore more than a relic. It is a living document, its initial message detailing the universe's birth, while its subtle distortions and hidden alignments record the entire history of cosmic evolution, from the first fraction of a second to the present day. Even a whisper can carry the weight of the cosmos. We have listened to the stories told by ancient light, but there is one final, profound whisper etched directly into the universe's first light, a whisper that confirms the presence of the most mysterious force of all. This is the integrated Sachs-Wolfe effect, a name that describes one of the most elegant cosmic processes we have ever uncovered. To understand it, picture the cosmic microwave background light on its 14 billion-year journey to our telescopes. As these ancient photons travel, their path is not through empty, flat space. They must climb in and out of the immense gravitational valleys created by superclusters of galaxies and the great dark matter filaments of the cosmic web. Think of rolling a marble up and down a series of gentle but vast hills. In a universe ruled solely by gravity and matter, this would be a fair exchange. The photon loses energy, red shifting slightly as it struggles uphill against the pull of a massive cluster. But then, it should regain that exact same amount of energy, blue shifting as it rolls down the other side. The net effect over the entire journey should be zero. The photon arrives with the same energy it started with, but our universe is not playing by those simple rules. We live in a cosmos dominated by dark energy, a force that causes the expansion of space to accelerate. This acceleration is constantly stretching and weakening the great gravitational valleys of the cosmic web. The hills are literally decaying and flattening out over cosmic time. So when a CMB photon climbs up a gravitational hill, it loses energy. But by the time it rolls down the other side, the hill has become shallower. It does not get all of its energy back. It arrives at our detectors ever so slightly colder, a tiny bit redder than it should be. Conversely, a photon flying out of a vast cosmic void, a great underdense region, experiences the opposite. It gains a little energy climbing out, and because the void is deepening due to the accelerated expansion, it holds onto that gain, arriving slightly warmer. This creates a specific, imprinted pattern on the CMB sky. When astronomers overlay a map of the CMB temperature with a map of the local large-scale structure of galaxies and voids, they find a faint but undeniable correlation. The cold spots in the CMB statistically align with the locations of massive clusters, while the warm spots align with the profound emptiness of the great voids. This correlation is the ghostly signature of the integrated Sachs-Wolfe effect. Its detection is more than just a curious pattern. It is direct, dynamical evidence for dark energy. It shows us that the gravitational landscape of the universe is not static. It is evolving in real time, or rather, in cosmic time. And we can witness this evolution by reading the subtle energy shifts in the oldest light there is. This effect transforms the cosmic microwave background from a static baby picture into a living chronicle. It records the entire growth history of cosmic structures, a timeline of how the universe built itself from tiny seeds into the vast web we see today. Every faint temperature fluctuation is a data point in that story, a whisper from the dark universe confirming that the fabric of reality itself is being stretched by a force we can only observe by its profound and ancient echo. Magnetic fields are a silent, invisible force woven through the cosmos. We find them on our own planet, within our sun, and spanning the vast disks of entire galaxies. Yet their influence may stretch even further, into the profound emptiness between these islands of matter. There is a growing conviction among astronomers that the cosmic web itself, the great dark scaffolding of the universe, is threaded with incredibly faint but pervasive magnetic fields. These are not the strong, structured fields of a galaxy, but a diffuse, cosmic hum of magnetism, a ghostly presence left over from the universe's earliest chapters. How could we possibly detect a magnetic field in what appears to be a perfect void? The key lies once again in the subtle behavior of light. When radio waves travel through a magnetized medium, their polarization plane slowly rotates, a phenomenon known as Faraday rotation. The greater the magnetic field strength and the more charged particles the light encounters along its path, the more this polarization twists. Astronomers can measure this twisting, known as the rotation measure, from thousands of distant quasars and radio galaxies scattered across the sky. By meticulously mapping these rotation measures, they are not just looking at the sources of the light, but using that light as a probe to feel out the magnetic fields it passed through on its billion-year journey to us. The resulting map reveals a stunning pattern. The rotation measures are not random. They show large-scale correlations across the sky, suggesting the radio waves have passed through a coherent, web-like magnetic structure that permeates the vast cosmic voids. The origin of these fields is one of the great open questions. Were they born in the turbulent hearts of the first galaxies and stars, then blown out by powerful winds to seed the intergalactic medium? Or are they a primordial relic, a fossil field generated in the universe's first frantic moments during inflation or phase transitions, and then stretched to cosmic proportions by the expansion of space itself. The specific patterns of polarization we observe, the subtle alignments and rotations, are the encrypted code that holds the answer. Deciphering this code will tell us if magnetism is a later addition to the cosmic story, or if it was a fundamental player from the very beginning, a hidden force that helped sculpt the cosmos we see today. Even the most energetic particles in the universe face a speed limit. Ultra-high-energy cosmic rays, protons and atomic nuclei hurtling through the void at nearly the speed of light, should not be able to travel very far. The cosmos is filled with a diffuse fog of light, the accumulated glow from all the galaxies across time. For a proton traveling at these fantastic energies, this faint background light is not harmless. It appears as a wall of high-energy gamma-ray photons. When the proton strikes one of these photons, it triggers a reaction known as the Greisen-Zatsepin-Kuzmin process. It is like a marathon runner constantly colliding with a dense mist, each impact slowing them down. This process should drain the proton's energy over a relatively short cosmic distance, creating a sharp cutoff in the energy spectrum we observe here on Earth. There should be a firm ceiling, a natural limit to how energetic any cosmic ray arriving from a distant source can possibly be. But the universe, it seems, loves to break its own rules. Experiments like the Pierre Auger Observatory have repeatedly detected particles with energies that soar beyond this theoretical cutoff. These are not just slightly energetic particles. They are cosmic cannonballs possessing energies millions of times greater than anything our most powerful particle accelerators can produce. Their existence is a profound anomaly. How did they get here with their energy intact? One possibility is that our understanding of particle physics simply breaks down at these extreme energies. The laws that govern these interactions in our laboratories may need a subtle rewrite when applied to particles traveling across billions of light years. Another idea is that these particles are not from far away at all, but originate incredibly close to us in cosmic terms, within our own local supercluster of galaxies. The challenge is finding an astrophysical object nearby that is powerful enough to create such unbelievable energies, a cosmic neighbor with an engine we have not yet identified. The most intriguing explanation, however, once again points to the hidden structure of the void. What if the intergalactic photon background is not uniform? We assume this cosmic fog is evenly distributed, but what if there are vast tunnels through the universe, regions where this background light is significantly thinner? In these directions, the marathon runner would face less resistance, allowing ultra-high-energy cosmic rays to travel much farther than our models predict without losing their punch. The detection of these anomalous particles, therefore, becomes a new kind of telescope. It does not see light, but rather the absence of light. It maps out the deep shadows and underdensities in the universal photon field, revealing a cosmos textured with immense, silent corridors where the fog has cleared, allowing the universe's most energetic travelers an unexpected path straight to our door. These cosmic strings would be the ultimate fossils, relics from a time when all the forces of nature were one. They are not made of matter as we know it, but are pure wrinkles in the fabric of space-time, formed when the infant universe underwent a sudden and dramatic phase transition, much like the way cracks form in ice as water freezes. A single string would be thinner than a proton, yet so incredibly dense that a mile of it could outweigh an entire mountain, and they would not have ends stretching across the cosmos in infinite or looped filaments. Their primary signature would be written in light. Because of their immense density, a cosmic string would warp the space around it with perfect, linear precision. If a distant galaxy were perfectly aligned behind one of these strings, its gravity would not create a smeared arc or an Einstein ring. Instead, it would produce a clean, sharp double image of the galaxy, a perfect pair of twins separated by a hair-thin, dark line in the sky. This is a signature unlike any other gravitational lens. Another telltale mark would be left on the cosmic microwave background. As the universe cooled and the CMB was released, a drifting cosmic string would have left a distinct scar. Its gravitational field would create a very specific, sharp step-like discontinuity in the temperature of the background radiation. A sudden jump from a slightly warmer region to a slightly colder one along a perfectly straight line. For decades, astronomers have been meticulously scanning sky surveys and CMB maps, searching for these linear patterns, these ghostly scratches on the face of the cosmos. The discovery of even a single cosmic string would be a monumental event. It would provide direct evidence for theories of grand unification and reveal the specific conditions of the universe in its first fleeting moments. It would be like finding the original signature on the cosmic birth certificate. This search for the most fundamental of cosmic threads, these perfect one-dimensional flaws in reality, compels us to look even deeper into the void, to ask what other primordial imprints might be hiding in the darkness, waiting to be decoded. Even the universe's baby picture holds a strange and unsettling gaze. When scientists created the most detailed maps of the cosmic microwave background, they expected a portrait of perfect randomness, a celestial fingerprint with no preferred direction. Instead, they found a ghostly axis. The largest and most fundamental temperature fluctuations in the ancient light are not scattered randomly across the sky. They show a subtle but statistically significant alignment, a preference for a specific plane slicing through the cosmos. This puzzling feature was nicknamed the axis of evil, a title that reflects just how deeply it disturbs our standard model of the universe. According to the foundational cosmological principle, the universe should be isotropic. On the largest scales, it should have no special direction, no left or right, no up or down in the cosmic sense. It should look the same in every direction, a uniform and homogeneous expanse. The axis of evil directly defies this expectation. It suggests that the cosmos might have a spine, a subtle architecture imprinted at birth that gives it a fundamental orientation. One immediate thought is that this is simply an illusion, a trick of perspective. Perhaps it is not the universe that is aligned, but our own motion through it that is creating a subtle smear in the data. Our entire galaxy is rushing through space, and this movement could potentially leave a dipole signature, a kind of Doppler effect on the ancient light. Yet, when researchers correct for this motion, the alignment stubbornly remains. Another possibility is local contamination, that light from our own galactic neighborhood is polluting the pristine signal from the early universe. But meticulous work has so far failed to find a foreground source capable of creating such a large-scale and specific pattern. This leads to the most profound possibility that the axis is real. It could be a fossil from the epoch of inflation, a scar from when the universe expanded faster than light. Perhaps the inflationary field that drove this hyper-expansion had a directional quality, a slight warp that was then frozen into the fabric of space-time and imprinted onto the first light. Alternatively, this preferred direction could hint that our universe is not perfectly smooth, but has a very subtle global rotation, or that it is shaped in a way more complex than we ever imagined. The axis of evil remains one of cosmology's most persistent and profound mysteries. It is a quiet warning that our most basic assumption about the cosmos, that it is fundamentally the same everywhere, might be an oversimplification. The universe's oldest photograph is staring back at us, and its gaze is not blank but directed. These faint whispers from the cosmos demand a new kind of hearing. Our current glimpse into these grand patterns is like trying to read a letter by candlelight, seeing only the boldest words. The next generation of observatories is poised to flip a switch, flooding the cosmic page with a brilliant, clarifying light. The James Webb Space Telescope acts as a time machine for infrared vision, capturing the light from the very first galaxies with stunning clarity. It will show us the infant cosmic web in its raw, initial state, allowing us to trace how its subtle gravitational pull began to shape the light of the ancient universe. We will see the dawn of the very structures that now imprint their signature on modern starlight. Meanwhile, on a mountaintop in Chile, the Vera Sea, Rubin Observatory will embark on an epic, decade-long movie of the entire sky. Its camera, the largest ever built, will not just take a picture. It will measure the subtle, synchronized warping of billions of galaxy shapes. This immense census of weak gravitational lensing will transform our shadowy map of the dark matter web from a rough sketch into a high-definition blueprint, revealing the true architecture of the cosmos. And listening to the universe's magnetic whisper will be the Square Kilometre Array, a colossal radio telescope spanning 2 continents. By mapping the rotation of polarized light from countless distant sources, it will trace the ghostly magnetic fields that thread the cosmic voids, potentially revealing if magnetism is a primordial force woven into the universe's first moments. Together, these instruments will turn today's intriguing statistical hints into undeniable, robust discoveries. The faint correlations and puzzling rhythms we now struggle to confirm will become the foundational data points for a new cosmology. They may validate our current ideas about dark energy and the cosmic web, or they could do something far more exciting. They could reveal entirely new classes of patterns, anomalies in the data that point to physical processes operating between the galaxies that we cannot yet even conceive. The universe has been whispering. Soon we will finally be able to hear the words. Galaxy clusters are the final word in cosmic structure, the titans of the visible universe. Their immense gravity binds thousands of galaxies together, and according to our leading model of cosmology, they should grow at a predictable pace over time. But one cluster in particular, nicknamed El Gordo, the Fat One, is a colossal exception to the rules. This behemoth, observed when the universe was only half its current age, possesses a mass that strains belief. In the standard simulations of the lambda cold dark matter model, a cluster of this immense size simply should not have had enough time to form so early in cosmic history. It is not alone either. A handful of other overly massive ancient clusters have been spotted, creating a distinct pattern of outliers that stand defiantly outside the predicted boundaries. What does this cosmic rebellion mean for our understanding of the universe? The light from the galaxies within El Gordo, and the way that light is distorted by the cluster's overwhelming gravity, tells a story of an unexpectedly rapid assembly. One possibility is that our measurements are subtly flawed, that we are overestimating the masses of these distant giants. But if the measurements hold, the implications are profound. It could mean that dark matter is not perfectly cold and collisionless as we assume. Perhaps dark matter particles can interact with each other through a force we have not yet detected, allowing them to clump together into massive structures far more quickly than our models allow. Alternatively, it might point to something exotic in the early universe, like primordial magnetic fields or a different type of inflationary physics, that gave these clusters a head start on their growth. El Gordo is more than just a record breaker. It is a cosmic stress test. Its very existence, written in the bent light of its captive galaxies, forces us to question if the foundational recipe for our universe, the precise mix of dark matter and dark energy we call LCDM, needs a crucial, unseen ingredient. This radical idea redefines the very nature of reality. The holographic principle proposes that our universe, with its rich three-dimensional depth, might be a magnificent illusion. All the information that describes everything within a volume of space, every star, every planet, and every one of us, could be entirely encoded on a distant two-dimensional surface, like a cosmic film projector casting the image we perceive as reality. Our four-dimensional spacetime, in this view, emerges from this underlying information, a holographic projection of data written on the boundary of the universe. What we experience as the tangible world would be a kind of shadow play, a consequence of quantum bits interacting on a surface we cannot see. This is not just a philosophical curiosity. It is a serious framework born from the study of black holes and the quest to unite gravity with quantum mechanics. It suggests that the fundamental building blocks of the cosmos are not tiny strings or particles, but bits of information. The patterns we have been tracing, the synchronized motions of stars and the aligned polarizations of galaxies, would then be the visible manifestation of this deeper informational code. They would be correlations written into the projection itself, hints of the underlying data structure from which space and time are woven. The search for observational evidence is incredibly challenging, but not impossible. If the holographic principle is correct, there might be a fundamental graininess to space, a minimum pixel size for reality, that could subtly affect the behavior of light over colossal distances. The way light from distant quasars interferes with itself, or the statistical correlations in the cosmic microwave background, could hold the faint, encrypted signature of this cosmic code. While still highly speculative, this perspective offers a potential explanation for why the universe appears so deeply interconnected on the largest scales. The ghostly alignments and rhythmic patterns in Starlight may not be messages passed through space, but rather artifacts of a unified origin, all part of the same holographic projection emerging from the two-dimensional edge of everything. Our own motion paints a fundamental pattern across the cosmos. The cosmic microwave background, that ancient afterglow of the Big Bang, is not perfectly uniform in temperature. It appears slightly warmer in one direction of the sky and cooler in the exact opposite direction, creating a vast thermal dipole that stretches across the heavens. This is widely understood as a cosmic Doppler effect. Just as an ambulance siren sounds higher-pitched as it moves toward you and lower as it moves away, the CMB appears warmer where we are rushing into it and cooler where we are fleeing from it. From this, we have calculated our solar system's velocity, a staggering journey of over 1 million miles per hour relative to this primordial light's rest frame. This dipole defines our ultimate cosmic reference point, the background against which all other motions are measured. Yet, a subtle unease lingers around this most basic of measurements. When astronomers compare the amplitude of this CMB dipole to other cosmic markers, such as the observed dipoles in the distribution of distant radio galaxies or quasars, a slight tension emerges. The numbers do not align perfectly. The motion we deduce from the ancient light does not quite match the motion implied by the modern universe. This discrepancy could be a simple statistical fluke, a mere wobble in the data. But if it is real, it points toward a deeper cosmic story. One compelling possibility is that we are feeling the gravitational pull of a local, unseen superstructure. A concentration of mass so vast and so close that its tug is subtly influencing our perceived motion through the cosmos. This hidden attractor, a great wall of galaxies or an immense dark matter halo we have not yet fully mapped, could be gently steering us, adding an extra component to our velocity that the CMB alone cannot explain. Alternatively, this tension might be a signature of the universe's intrinsic graininess on the very largest scales. Perhaps the cosmological principle, the idea that the universe is smooth and homogeneous, begins to fray at the edges of the observable cosmos. The dipole anomaly could be a whisper that the distribution of matter and energy is not perfectly even, that there are grand waves and troughs in the cosmic ocean that imprint their own unique signature on our motion. The very definition of our cosmic rest frame, the foundation for how we measure everything in the universe, might therefore still hold profound secrets about the true, large-scale flow of matter and the ultimate structure of reality. These intricate patterns lead us to a question that echoes far beyond the data. Why does the universe appear so perfectly calibrated for our existence? The fundamental forces, the masses of the basic particles, even the initial energy of the Big Bang itself, all seem balanced on a razor's edge. Alter any one of these constants by even a tiny fraction, and the cosmic story would be vastly different. Stars might never form, complex atoms like carbon would fail to exist, and the universe would be a silent, sterile void. This remarkable fine-tuning is written into every pattern we have observed, from the specific fluctuations in the cosmic microwave background to the very existence of the elements that make up our world. The Holographic Principle offers a way to contemplate this puzzle. It suggests a simple yet profound idea. We observe this particular universe with its specific set of rules for one fundamental reason, because it is a universe capable of producing observers like us. In a cosmos where the physical laws are just slightly different, no one would be around to notice. This perspective does not explain why the laws are this way, but it reframes the question of why we see what we see. One compelling way to visualize this is through the concept of a multiverse. Imagine our universe is just one bubble in a vast cosmic foam, where each bubble has its own unique set of physical constants. Most of these bubbles might be stillborn or chaotic, utterly hostile to any form of complex structure. But in a few rare bubbles, the numbers line up just right, allowing for galaxies, stars, planets, and eventually, life to emerge. We find ourselves in one of those rare, hospitable bubbles not by chance, but by necessity. It is the only kind of place we could possibly be. This principle reminds us that our role as observers is not separate from the cosmic landscape we study. The patterns we meticulously catalog are not just a random sampling of all possible universes. They are a filtered view, a self-selected portrait of a reality that allows for contemplation. So when we trace the great cosmic web or decode the whisper of gravitational waves, we are not just mapping the universe. We are reading the unique user manual for a reality that, against staggering odds, learned to read itself. Our journey through the whispers of Starlight has painted a cosmos of breathtaking interconnection. Each pattern we have traced, from the ghostly alignments in polarized light to the rhythmic dimming of ancient quasars, is a luminous signature of processes operating in the great dark between the galaxies. These are not mere curiosities. They are fundamental challenges to our standard models of cosmology and particle physics, pushing the very boundaries of what we know. The consistent, profound theme is that no star is an island. The light from a distant quasar carries a diary of its epic voyage, its pages filled with entries from every gravitational field it felt, every magnetic domain it crossed, and every particle cloud it penetrated during its billion-year journey. This light is a collective memory, a narrative of the entire cosmos. As our technology advances with observatories like the Vera Rubin and the Square Kilometre Array, these faint patterns will sharpen from statistical whispers into clear, undeniable voices. They may reveal new forces that sculpt the cosmic web, new components of the universe hidden in plain sight, or even new dimensions of reality itself. The cosmos is not silent. It is speaking to us through the ancient language of light. Our great and ongoing task is to continue learning how to listen.